Number 3. If you roll a fair die, find the probability the number is even, the probability the number is less than 3, and the probability the number is even or less than 3. Alright, so because this situation is different from our previous problem, now we're working with a die. Now this is just going to be a regular 6-sided die, so you know that you have the numbers to work with, which are 1, 2, 3, 4, 5, 6. Okay? The probability the number is even. If we take a look at our set here, we can see that we have even numbers of 2, 4, 6, and we have, so right there we see that there's a total of 3 possibilities that are even out of a total of 6 possibilities overall. And so we see that we have a 1 in 2 chance of getting an even number on a die. The probability the number is less than 3. So if we take a look at the probability is less than 3. Keep in mind, less than does not mean less than or equal to. So you really just have the numbers 1 and 2. So because of that, you only have a 2 in 6 chance of getting a number less than 3. And 2 out of 6 is basically the same as a 1/3 probability. The probability the number is even or less than 3. Okay, so now we're dealing with two events rather. We can say that the number is even. Maybe we can classify that as event A. Or the number is less than 3. Let's call that event B. Now, if we call it A or B, if we call the events A and B, then you're actually kind of, you can actually relate this to something that we have seen in the past, not too long ago actually, where if you want to find the probability of events A or B occurring, recall that another way that we can write this is by saying probability of A, and then the symbol we use there is that union symbol B. Right, so it's the same idea, and we actually had a formula associated with this. We knew that based on Venn diagrams, we can say, well, that's the same as taking the probability of A, and then we combine that with the probability of B, right? If you remember our Venn diagrams, we have probability of A plus the probability of B, but we accounted for that intersection 2 times. So what we want to do is take away the probability of A and B, or let's actually do the intersection symbol rather, A and B, A intersect B. And then we can just plug in our numbers, plug in our probabilities, and find the probability of A or B. Okay, so if we take a look at the values that we have here, the probability of A, the probability of the number is even. Oh, wait, we found that out before, didn't we? We said that that probability is 1/2. Okay, now I'm actually going to write it in its unsimplified form, 3/6, because as I think ahead, I actually realize that the probability of B, which is less than 3, we also have a total number of outcomes as over 6. So that way I have common denominators. So there I see 3/6 plus 2/6. And what we want to do is take out the probability that a number is even. And keep in mind, if I were to write this in words actually, the probability that you have an even number and the number is, I'll just do notation here, is less than 3. Okay, so if I were to look at my numbers up above again, what do we have? Even numbers are 2, 4, and 6. And then also we need that number to be less than 3, so here it is. And you have to satisfy both criteria. The only one that satisfies both criteria is this number right here, right? The 2. And so therefore you only have a 1 in a total of 6 chance of getting a number that's even and less than 3. Okay, so now in doing the math here, we can find the probability of getting an even number. I'll just write the words out. Even or less than 3. It looks like our probability is going to be 3 plus 2, 5, 6, minus 1 is 4, 6, or that also simplifies to 2/3, just like that. Okay. So I believe that will now bring us to, again, the formula that we have seen before. The probability of A or B is equal to, well, the notation of that would be the union symbol. Probability of A or B is equal to probability of A plus probability of B minus probability of A and B. Okay. Now, what would happen if A and B actually did not intersect? If you notice, these two circles, we don't have anything in common among them. then the probability of A and B, well, there's nothing to intersect with them, so that probability would actually be 0. This tells us that A and B have nothing in common. That's basically what it's saying. Okay, and so if there is nothing in common, we've discussed this word in the past actually in a previous video, but these two events are basically called mutually exclusive events. Another word for this, you can call this independent events as well. Independent events. Okay, so mutually exclusive or independent events. All right, we have another problem here. The odds favoring the incumbent winning the election. So in this case, you know, in 2020, we have the incumbent being the basically the president who is running for office again. So in this case, this incumbent would be Donald Trump. Winning the election are 2 to 3. Now, because of the way it's phrased, the odds favoring the incumbent winning means that the incumbent, or in this case, President Trump, has a chance of winning that is represented by the number 2, and a chance of losing by represented by the number 3. So he has a 2 to 3 chance of winning, basically, telling us that you can see here with 2 and 3, you have a total of 5. So 5 is like your total possibilities, kind of. Okay, so if that's the case, what's the probability that the incumbent wins? Well, the winning part of our ratio here is the 2, so the incumbent has a 2 in 5 chance of winning. So therefore, if the incumbent has a 2 in 5 chance of winning, that must also mean that the incumbent also has a 3 in 5 chance of losing. What does it mean if the incumbent loses? That means that the challenger wins. So the probability the challenger wins is also the same result. It's going to be 3 out of 5. Okay. Number 5. A die is rolled, then a coin is tossed. Oh, this is a bit of a different problem. Notice how we now have two unique scenarios. One is dealing with a die, and the other is dealing with a coin. But we can still set up our problem the way that we had in the past. Many ways to set up probability problems is by using, let's say, tree diagrams, right? You can do tree diagrams with this. Now, if you roll a die, again, we're just dealing with a normal 6-sided die, so the possible outcomes that we have would be the numbers 1 through 6. So I'm just going to go ahead and label that. And as a tree diagram, I'm just going to go ahead and branch out all of those numbers. Okay? And then with each of those possibilities, keep in mind that you also are flipping a coin. So let's say you roll a 1 on the die, and then you flip a coin. Well, if you flip a coin, you only have a choice of heads or tails. So for each of these possibilities, you can write down heads or tails and branch your tree diagram into 2 parts for each selection. Okay, there we go. All right, and then from there, we can now, part B, find the probability that the die's number is even and the coin is heads. So I'm going to go ahead and just circle this in a different color here. So if we want an even number, we're looking for 2, and then we also want the heads. So 2h would be what we want. What else is even in heads? Well, we would want 4 in h, and another even number in heads would be 6 in h. So it looks like we have a total of 3 out of, how many things do we have? 2, 4, 6, 8, 10. We have 12 possibilities. So there's 3 in 12 chance of getting an even number and the coin is heads. Or in this case, if we simplify that, we have basically a 1 in 4 chance, just like that.